everyone. Hello, everyone. Good afternoon. Okay, so I think most of the class is here. 28. Now let me call your names for to take your attendance. So if you're here, just let me know in the message box. Okay. Right. Brenda. Brenda, are you here? Okay. Chen Supian. Chen Supian. Tia Chai Siu. Chu Zhang Heng. Choi Yu Yang. Choi Yu Yang. Ernest. Go Kian Sing. Okay. Hu Hing Tong. Right. Ku Bun Kyung. Ku Bun Kyung. Lau Lok Ching. Lee Zilin. Lim Chun Wei. Lim Wen Yang. Lim Wen Yang. Lim Yong Chuan. Okay. Long Yao Ting. Lo Tiong Lia. Okay. Lu Chui Min. Lu Chui Min. Ng Han Xiang. Ng Wei Hong. Ong Mei Lin. Hong Sui Wen. Kwa Yi Hang. Kwa Yi Hang, are you here? Soyan Cheng. Good afternoon. Tan Xin Chen. Okay. Teo Leong Ho. Teo Leong Ho. Teo Yi Si. Wong Chung Yi. Good afternoon. Wong Ka Sing. Right. Yong Wing Liang. Teo Leong Ho is here. Okay. Yong Chi Ye. Yong Chi Ye. Okay. Hua Yi Hang, are you here? Hua Yi Hang. Hua Yi Hang. Lim Wen Yang. Lim Wen Yang, are you here? And Ku Bun Kyung. Ku Bun Kyung, are you here? Okay, I'll call your names. Please remind me to check your attendance again at the end of the class. All right, so today we are going to review the materials, lecture materials, the lecture videos, right? Very interesting topic on interrupts. Interrupts is the heart of microcontrollers, right? Interrupt is the mechanism that allows your microcontrollers to respond quickly to any events that happen. And interrupts is what made the ARM Cortex processors so popular, so powerful because of the interrupt system. And we shall see shortly why it's so good. Why people don't use PIC microcontrollers anymore. They use ARM Cortex M microcontrollers. Okay, for more performance and responsive applications. Of course, PIC microcontrollers are still used for the application is low power. Okay, PIC microcontrollers are used when low power and low cost is very important, and it is so that's why you have different market segments. Okay, you have the low power, low cost market, and then you have the higher performance, more responsive applications market. That's where the ARM Cortex M is, right? Low cost, low power is PIC microcontrollers. Okay, so let's start with the interrupt system. Okay, interrupt system. So that's about page 15, I think. Yes, exactly. Okay. Right. So now I've drawn a nice block diagram of a microcontroller here. Right. A microcontroller consists of basically three main things: the processor, peripherals, and memory. I didn't draw memory here because memory is not relevant to the interrupt system. So the other two most important components are peripherals and the processor. Okay, so peripherals they can interrupt the processor. Peripherals run together with the processor. We say in parallel, right? So while your processor is executing instructions, right? Executing instructions, the peripherals can all run in parallel together with the processor. For example, the peripherals can be counting time if you have timers, or the peripheral can be detecting some inputs from your I/O port. Okay, or your peripheral can be doing an analog to digital conversion or a digital analog conversion. So basically, all these peripherals they run in parallel with the processor, right? They run in parallel with the processor. Okay, so what happens is they can disturb the processor. So the processor is happily just executing instructions in the main loop. You know, you're looping, doing something. and the processor can be interrupted by peripherals. How? Peripherals can send an interrupt signal to the processor. So who filters these interrupt signals before they can wake up the processor? That is before they can disturb the processor, and that is the interrupt controller. Okay, the interrupt controller. So the interrupt controller decides, okay, this peripheral wants to disturb the processor, can pass through or not, can or not. Should I allow the interrupt to pass through? In other words, is the interrupt enabled? We do this in the interrupt controller. So today, this is the main character. We're going to look at this yellow color block, the nested vector interrupt controller. Okay, before that, um, Wen Yang. Okay, Wen Yang is here, right? Okay, so this guy, he is called a nested vector interrupt controller because you can do interrupt nesting. Oh, that is something new, right? Interrupt nesting. Interrupt nesting, that's something new. Okay, so what's so good about interrupt nesting? Now, I bring your attention back to PIC microcontroller. PIC microcontroller, right? When an interrupt happens, your processor will run the interrupt service routine, right? When an interrupt happens, your processor will run the interrupt service routine. Okay. What if another interrupt happens? Can your processor respond? Class, let me ask you this question. If you are using a PIC microcontroller, right? Your processor is responding to an interrupt. So you're executing the interrupt service routine code. Okay. What happens if another interrupt comes? Yes, class. Any volunteers? Can you give me an idea? No right, no wrong answer one, don't worry. Q. Q means basically the in a PIC microcontroller, if the processor is currently responding to an interrupt, that means the processor is executing code in the interrupt service routine. Another interrupt comes along, you say Q, right? Yeah, that's correct. The idea is correct. The processor won't respond to that interrupt until it is done with this one, the current one. So we say the other one is queuing, or a better word is pending. The interrupt is pending, is waiting. Okay, so there is no concept of priority. There is no concept of priority. That means, for example, right now, right now you're talking to your friend, right? Then a very important person uh, call you. So you see his call, your phone can see. This very important person whose phone call you have been waiting for 2 weeks already, very important. So obviously you will tell your friend, okay, please hold while I answer this other more important call, right? So we have the concept of priority. If another interrupt comes that is more important than the current interrupt, obviously the processor should respond to the more important interrupt first, right? So we call that interrupt nesting. Okay, and this is supported by this NVIC, nested vector interrupt controller. That's what the nested means. So the processor can have different levels of interrupt. A higher priority interrupt can take over the processor from a lower priority interrupt. In other words, we say in layman English, a more important interrupt can interrupt the less important interrupt. Okay, something like that. So that's what nesting is, interrupt nesting. Okay, so how does the NVIC do this? The NVIC, right? He got these three registers. NVIC is just like any microcontroller peripheral. When you program a microcontroller peripheral, you just set and clear bits in their control register, right? NVIC also got control register, okay, which allow us to do three things like enable, disable, enable the interrupt or disable the interrupt, set or clear the pending status. The interrupt just now we say can be pending or waiting to be serviced, right? So you can make an interrupt pending, or you can remove it. You remove its pending status, and you can also set the interrupt priority. Priority. This is what determines nesting. Who is more important? How we do this? Okay, let's look at the NVIC instruction registers. So these are your NVIC registers. These guys, right? So you got enable, disable. You have this register called interrupt set enable. set to enable. So you have 31, 32. You have 32 interrupts. You got 32 interrupt sources. From your microcontroller supports 32 interrupt sources. That means okay, GPIO port is one interrupt source. ADC is another interrupt source. Timer is another interrupt source. So it can support a maximum of 32 interrupt sources. Okay, so 0 represent interrupt 0. 1 is for interrupt number 1 until 31 is for interrupt number 31. So you got total of 32 interrupts. Interrupt number 0 to interrupt number 31. So which interrupt is which? That means, for example, I ask interrupt number 15. This is for which interrupt? Then you have to look at the startup file. Okay, if you go to the startup file or you go to the device header file, the LPC17XX.h or the STM32F10X.h, that device header file, you will find inside the device header file, it will tell you interrupt number 15 is for which microcontroller peripheral. For example, interrupt number 15 is for GPIO interrupt, something like that. So basically these 32 interrupt sources that correspond to specific microcontroller peripheral interrupts. And you can put a 1 here to enable it, or you put a 1 at the IC, interrupt clear. Put a 1 here to disable it. Okay, so this is to enable, this is to disable. You write a 0, got no effect. You must write a 1 for to have effect. Okay, all right. Then we look at the pending status. So similar to set to enable and disable, you can set the pending and clear the pending status. ISPR interrupt set pending, ICPR interrupt clear pending status. Okay, now the more important one to talk about is this guy, the priority register. So you got IPR interrupt priority 0 to 7. So you got 8 interrupt priority registers, right? Why 8? That's because the priority is 8 bits. Okay, priority is 8 bits. So interrupt priority register 0 stores the priority for 4 interrupt sources. Interrupt source 0, 1, 2, and 3. And each interrupt source, the priority got 8 bits. That means you can set 256 interrupt priority levels. Okay, you can set a maximum of 256 interrupt priority levels. And the smaller the number, the higher the priority. Okay, the smaller the number, the higher the priority. So if you put 0 here, that's the highest priority. You put 255 is the lowest priority. So you put a number here, it will be the priority for interrupt 0. You put a number here, it will be the priority for interrupt 1, and so on. So you have 8 registers because we have a total of 32 interrupts, 32 interrupt sources. Okay, so this is how you control the NVIC. Let's go back up to the NVIC. Okay, let's go back up to the NVIC. All right, so this guy, now you know now you know what the nesting means, nested. How about the vectored V? This interrupt controller also automatically, it will automatically branch to the correct interrupt service routine. Okay, you see in your PIC microcontroller, when an interrupt happens, your processor will go to the interrupt vector at address form. I just a refresher, For PIC microcontroller, when an interrupt happens, your processor will always go to address 0x4. This is fixed. No matter which interrupt it is. PIC microcontroller got many interrupts, but it doesn't matter which interrupt it is. Your processor will always go to the interrupt vector at 0x4. So then you will have, no choice, you have to write code there to check who caused the interrupt, right? Because PIC microcontroller got many interrupt sources. So an interrupt happens, your processor go to the interrupt vector, 0x4. You have to write code there to say who caused the interrupt, right? You don't know. But the vector V here, vector means the processor will automatically run the interrupt service routine code for the interrupt, the correct ISR for the interrupt. You don't need to check, right? Here is how it happens. Now, in your memory, at address 0, this is fixed, okay? In memory at address 0, the first 4 bytes is the initial stack pointer value, right? This is the initial stack pointer value. Because of when you start up your microcontroller, the microcontroller will come here and fetch this value to initialize the stack, right? Why do we need the first thing that you do? When you wake up in the morning, the first thing that you do, all of us got different first things that we do, but definitely there's something, the first thing that you have to do, right? So same with the microcontroller, when you turn it on, the first thing it has to do is it has to fetch the stack pointer and initialize the stack. Why? Because interrupts can happen at any time. An interrupt can happen the moment you turn on the microcontroller. Right? Interrupts that can happen at any time. Interrupts can happen the moment you turn on the microcontroller. Okay, and we need the stack to respond to interrupts correctly. The stack must be initialized to respond to interrupts correctly. Okay, so that is why, because interrupts can happen at any time, interrupts can happen the moment you turn on the microcontroller. We need the stack for interrupts to work correctly, so we have to initialize the stack first of all. It's automatic. So when you turn on the microcontroller, processor will come here. It will fetch these 4 bytes and put it into the stack pointer. So the stack will be initialized. So that means the stack is starting from somewhere. Yeah. You put some value into the stack pointer. So the stack pointer will be pointing to this value in memory, this address. That means the stack initialized already. Okay. Then the next 4 bytes is the reset handler. That means the code to deal with a system reset. That means this is the code that you run first of all. So the processor will fetch this. This is address. This is the address of the reset handler. Processor will fetch this and run this and run the code that should be run when your processor starts. Okay? We call it the reset handler. Now, what are the rest of the things in this vector table? We call this a vector table because this is actually addresses or vectors of interrupt service routines. So reset handler is a interrupt service routine. The interrupt is reset. Then you got non-maskable interrupt, hard fault, and so on. Supervisor call, pendable supervisor call, sysdig timer interrupt. And then this is your microcontroller peripheral interrupt number 0 to 31. Okay, this is your microcontroller interrupt source interrupt number 0 from the source number 0 to 31. So you have 32 microcontroller interrupts. Right below here, these are called system exceptions. Basically, all these guys they will disturb your processor. Okay, so when any of these happens, the processor will come to this vector table and it will fetch the correct address. So for example, if interrupt number 2 happens, processor will come to this vector table. Automatically, it will come here to IRQ number 2 here, and it will fetch this address. So this is the address of your interrupt service routine for IRQ2. You come here and fetch automatically. So that's why we say uh, vectored interrupt controller. So nested because you have interrupt nesting based on priority. Vectored because the processor can automatically fetch the interrupt vector and go to the correct interrupt service routine. Interrupt controller IC because you can enable, disable interrupts individually, set their priority, and also set and clear their pending status. Right? So that's what NVIC means. Okay, so the NVIC's job is to manage exceptions. Exceptions are things that can happen at any time. Why do I always say can happen at any time? Because you see, in a processor is a digital system. Digital systems only do something or change state when there is a clock pulse. Imagine, think of your counters. Last time digital electronics, you learn up counter, down counter that you build using JK flip-flops or other types of flip-flops. If there is no clock, the counter don't do anything, right? When you have a clock, only the counter will count up or count down, right? So it's the same with the processor. Your processor don't do anything when there is no clock signal. So the processor will do something when there is a clock signal and then wait until the next clock signal, you do something again and wait. Until the next clock signal, you do something again and wait like this. So all processor activity is based on clocks. No clock, no activity. But exceptions, they are not bound to clocks, right? Exceptions are they are not tied to clock signals. Exceptions can happen at any time, right? And exceptions are there are three categories. You got interrupts, which come from microcontroller peripherals. Basically, we say interrupts are the signals that come from outside the processor. Outside the processor, we call them interrupts. Things that come from inside the processor, we call them exceptions, or specifically system exceptions. These are the signals that come from the processor itself. For example, the processor detecting something that's not supposed to happen, okay? And then it will inform the NVIC. For example, this is, I don't talk about this because you don't know about privilege yet. I'll talk about this later. But you have something called privilege and unprivileged. Okay, so unprivileged means you have no right, no authorization. So the code that without authorization, if it tries to access some memory location that requires authorization, then it will generate a system exception. Okay, this is for security one. Okay. And then you have faults, error conditions, things that the processor is not supposed to do. So if the processor do them, then it will trigger a fault. So when you trigger a fault, where do you go? If a fault is triggered, that means the processor detects itself doing something it's not supposed to do. The processor will then come here to this interrupt service routine called hard fault, right? So then you can put some code here to help the processor recover from the fault. For example, just reset the whole microcontroller. But normally, we use this for debugging. Okay? We use this for debugging. Normally, we put a breakpoint. Normally, we put a breakpoint inside the hard fault handler. We put a breakpoint inside the hard fault handler. So if a fault happens, your processor will come to the hard fault handler, right? Then execution will stop because we put a breakpoint inside. This is how we trap errors. So when we run our simulation, if any errors happen, processor execution will immediately stop in the hard fault. Okay, so you know, oh, an error has occurred, and you can backtrack. You can backtrack and find what is the source of the error. Otherwise, it's very difficult to find and fix errors. The hard fault, putting a breakpoint in the hard fault, allow us to stop execution the moment an error occurs. Okay, what is an error? This one, we talk about this on week 12. What is an error? Is everything is finite. You have a one whole page with around 10 to 20 conditions. There's a complete list of all the conditions that will cause a fault. I just put a few here, right? For example, the processor execute an undefined instruction and so on. So you have a complete list of all the faults that will, all the conditions that will trigger a fault. Okay, so what happens? What happens when an exception comes along? What happens when an interrupt, system exception, or fault, all these? What happens if they come along? The processor will stop normal execution, and then it will branch to the interrupt service routine, right? We call that is interrupt service routine, a special code segment. So we got different names, terminology. If interrupt, you call it interrupt handler or interrupt service routine ISR. If it's a system exception, you call it a system handler. If it's a fault, you call it a fault handler. Just a name, this terminology. Basically, handlers. Okay. And the address of these handlers are inside uh, the vector table. Okay, inside the vector table. Now, these interrupts, they have specific numbers. You got number 1 to 47, right? So reset is interrupt number 1, non-maskable interrupt is interrupt number 2. You got numbers 1. These numbers are placed into your IPSR. This guy, page 16. Okay, this guy. Remember this guy? We are now at the first slide. You saw this last week. Exception number. So this interrupt IPSR, this guy inside your program status register, he will hold the exception number of the exception that the processor is currently responding to. Okay, so this is for debugging. Let's say when you're debugging, so you want to know which interrupt is my processor responding to now. Then you just go to the IPSI and check the number there. Okay, then you will know which interrupt your processor is responding to. Okay, now these interrupts, right? they have a priority. Some are fixed. Some interrupt priorities are fixed. Some are configurable. Configurable means you can change the priority. So this is your 8-bit priority value. Just now you saw the interrupt priority register, the NVIC register, the interrupt priority register. This guy, the interrupt priority registers. So each interrupt has an 8-bit priority. So let's look at this 8-bit priority now. Okay, let's look at this. Let's look at this 8-bit priority now. So uh, programmable priority is 0 to 255, right? These are programmable. Then you have fixed priority. Uh, Hard fork is -1, unmaskable interrupt is -2, reset is -3. Not because negative number got any meaning. It's just that because configurable start from 0, then higher priority than 0, they just put negative. This is no meaning on it. It can be 1, 2, 3, and then this is 4 to 258. But isn't it nicer you put 0 to 255 and then this one logically we'll just put -1, -2, -3, smaller number. Okay, right. So configurable priority, you got 8 bits, but not necessarily all 8 bits are used. This depends on the microcontroller vendor. Some will just implement 2 bits, some implement 4 bits, and so on. Okay, but if you look at the architecture, ARM version 6M, which is Cortex M0 and M1, they only support 4 levels of priority, which is at the most significant bits here, 0, 0, 0, 1, 1, 0, 1, 1, which corresponds to 0, 64, 128, 192. Okay, but ARM version 7M, which is your Cortex M3, M4, M7, supports the full 8-bit priority. Now, this 8-bit priority can be split into 2 parts. Okay, we call this the group priority and this one the sub priority. Why split? The group priority determines preemption. Preemption. Preemption means, right, can take over or not. Okay, just now I say if the processor is currently executing a lower priority interrupt, then a higher priority interrupt comes, the processor will stop responding to the lower priority and it will respond to the higher priority, right? This means that the higher priority has taken over the processor from the lower priority. This act, we call it preemption. Okay? Preemption means processor stop executing a lower priority handler to run a higher priority one. So when you have preemption, then you got interrupt nesting already. Okay? So preemption, we have to look at group priority. If 2 interrupts they got the same group priority, means no preemption. Okay? If 2 interrupts they happen at the same time, both from the same group priority, right? Then who go first? Then we look at the sub priority. Right? So group priority is for preemption. If 2 interrupts happen at the same time, then the smaller number will go first. The smaller group priority number, smaller the number, the higher the priority. Smaller number go first. But if 2 interrupts happen at the same time, same group priority, then who go first? We look at the sub priority. Okay, right. So now we know about all this already. Let's look at the sequence. Let's look at the interrupt sequence. How does the processor respond when an interrupt comes along? The interrupt sequence. Okay, it's the interrupt sequence. Okay, so now when an interrupt happens, it needs to be sampled. Your digital signal processing, DSP. When something happens, your processor will not know until you sample it, right? So sampling is bounded to your CPU clock, right? Sampling only happens during the CPU, during the low to high or high to low of a CPU clock, So if an interrupt signal comes along, yes, the NVIC will receive the signal, but the processor won't respond until it's detected when the signal is sampled. Okay, so during the CPU clock cycle, when it's detected, then the processor will start responding. So that's why if your interrupt can be a pulse or a level, the interrupt signal can be a pulse or a level. If it's a pulse, it needs to be minimum 1 processor clock cycle. Otherwise, the processor may miss it. If it's less than 1 cycle, the processor may miss this interrupt. Okay, it may miss it. Right. So what happens after the interrupt comes? As a pulse or a level, what happens after it comes? the processor will then record it in the pending status register. So the pending status register is like a recorder, a logbook lah, right? If the interrupt comes, it's a pulse. The pulse comes, it will come and go, right? Once it's gone, you don't know it happened. So if the interrupt is a pulse, it comes, it will be recorded in the pending status register. But just now you saw, the pending status register only got 1 bit for each interrupt, right? The pending, whether this interrupt is pending or not, you only got 1 bit, So that's why even if the pulse happen a few times or you pulse a few times, or it will just be interpreted as one interrupt request, IRQ, interrupt request as one, because the pending bit is only one, right? You cannot record more than one occurrence, although it pulse a few times. Okay, right. So the pending status register will record that the interrupt has happened. Then the processor will have to check some conditions to see whether this interrupt should be responded to or not. Okay, what are the conditions? First of all, you are not stopping the processor. Now, if you connect a debugger to your processor, a debugger, right? Debugger can stop your processor. Simulator, you can make your code run line by line, right? If you have a debugger, you can stop the processor execution and then make the processor execute line by line of code. So we call that the CPU is halted. Okay, so the CPU is not halted. The interrupt is enabled, right? Just now the interrupt enable, disable, right? You enable it already. It has sufficient priority. Nobody that has higher priority is running now. It has sufficient priority. And the priority mask is clear. Remember this priority mask? This register is the global interrupt disable. So if this register is a 1, then all interrupts will be disabled. This register is like your fuse box. In your house, you got this fuse box, the big fuse. If you close the big fuse, no power to your house, right? So this is the big fuse. Right? And then the interrupt enable disable bits, those are the small fuse. This is the big fuse. Okay, so if all this is satisfied, then the exception is accepted. Then we start to do automatic stacking. This stacking is very important. Why? Because your processor uses these registers R0, R1, R2, R3, R12, LR, PC, and XPSR. Processor use these registers. So if you're running some background code, you're running some code in your main loop, there will be some values in these registers. Okay, if an interrupt happens, your processor will then stop running the main code and run the interrupt service routine. The interrupt service routine will also need to use these registers. Therefore, before we run the interrupt service routine, you need to save these registers, the values of these registers being used by your main programmer into the stack first before you run the interrupt service routine. Okay? So this is called stacking, and it's automatic. It's automatic. So that's why you have a bit of interrupt latency, some delay. So different Cortex-M, you got different number of cycles of delay, but it's fixed. Okay, it's fixed. Assuming zero wait state memory means that the memory and the processor is always at the same speed. Same speed, or memory is faster than the processor. So the processor never need to wait for memory. If you go above 50 megahertz, memory, most of the time, maximum speed is 50 megahertz. If your processor is running higher than 50 megahertz, that means your processor is faster than memory. When this happens, processor needs to wait for memory because memory is slow. Okay, so assuming zero wait state memory, that means processor never need to wait for memory. Then you will have this number of cycles to perform this, to do all these things, check the condition and do automatic stacking. Okay, so when we stack, right, we call this the stack frame. These 8 registers is the stack frame. They must go into memory at an address divisible by 8. So if you remainder with 8 is divide by 8, remainder is 0. We say divisible by 8. This is a requirement. Right, for code to work correctly. We divisible by 8 bytes. 8 bytes is 2 words. One word is 4 bytes. 2 words is 8 bytes. Okay, so 8 byte, 2 words, we say double word alignment. You see this very often. The stack is always double word aligned. That means aligned to 8 bytes. Okay. Now, if it's not aligned to 8 bytes, that means when you take the stack pointer divide by 8, you get 4. Then padding will have to be inserted to make the stack frame when it goes in divisible by 8. Okay, padding must be inserted. So if padding is inserted, then your XPSR bit 9 will become 1 to indicate that padding is inserted. Because later when you unstack, you have to remove the padding. Okay, you see, now we are stacking, right? Later we will need to unstack. When you return from the interrupt, you need to unstack. So when we unstack, we also need to remove the padding. So you have to record that you padded already. So XPSR bit 9 indicates padding. If 1 means got padding. Okay, all right. So after stacking is done, the processor will switch to handler mode and use the main stack. Now we have 2 stacks. All right, your microcontroller got 2 stacks: process stack and main stack. Why we have 2 stacks? This is for operating system, which we will talk about on week 7. But I just tell you the reason why. You see, operating system, you got user code and the operating system code. Right? OS code, operating system, OS code, and user code. We need to separate them. Operating system code uses its own memory. User code uses its own memory. Why we need to separate that? So that the operating system code can terminate user programs if got any error without affecting itself. Okay. For example, my brain, if my right hand side is for the operating system, left hand side is for the user code. If any of the user code got error, I just flush the left hand side of my brain, flush it, and then reload the user programs without affecting my right hand side because we separate the brain. Okay. So we use separate stacks. But when you are responding to interrupts, right? When you're responding to interrupts, you always use the main stack. So when before you run the exception handler, the processor will always switch to use the main stack. We say it is in just a name now. We say handler mode. Okay, so got 2 modes. You got thread mode and handler mode. Thread mode is when you are running user code. Handler mode is when you are running interrupt code. Okay, and when you are in handler mode, you always use the main stack. So the stack pointer is loaded with the main stack pointer value. Okay, and then the address is fetched. The address of the interrupt series routine is fetched with step vector fetch. After you fetch the vector, you load it into the program counter. Not you, sorry, not you. This is all done automatically. So the address is loaded into the program counter, and the next thing that happens would be the exception handler starts to run. Okay. Now, at the same time that the exception handler starts to run, the pending bit will be cleared automatically. Pending bit will be cleared, and then the interrupt that is currently running, the number will go into the IPSR, and then your link register will get a very special value called the exception return code, EXE return code. What's this? What's this? This is very important. This exception return code that is automatically placed into the link register. Why? Now, how do you return from interrupt? PIC microcontroller, if you return from interrupt, you use RETFIE, return from interrupt instruction. So there is a special instruction that allow you to return from interrupt. So other microcontrollers or other processors, all of them got a special instruction to return from interrupt. For ARM Cortex M processors, the mechanism to return from interrupt is not an instruction. It's this code, exception return code. So if you want to return from interrupt, what you do is you take the exception return code, you load it into program counter. See, at the start, this exception return code is stored into the link register, right? It's stored into the link register. So you just take the link register, which holds this exception return code, you load it into program counter. When you load this value in link register, you load it into program counter. How BXLR, BXLR, branch and exchange. Put the contents of LR into program counter. So when program counter gets this value, it's very special one. This exception return code. All right. this address 0xf don't exist one. This address don't exist. So when you put this address into the program counter processor will never go to this place to fetch instruction. Processor immediately know that this is the exception return. If it sees 0xf something, is exception return. Okay, so what's this in this exception return code? The important bits are these two bits, bit 3 and bit 2. The rest all not used. It's only these two bits that are important, bit 3 and bit 2. Bit 3 will tell the processor, are you returning to handler mode or are you returning to thread mode? If you're returning to handler mode, means that you have interrupt nesting, right? If now you are in handler mode, you return back to handler mode, means you must have interrupted another interrupt just now. That means interrupt nesting. If you return to handler mode, that means interrupt nesting. If you return to thread mode, that means no more interrupts already. Okay. And then this one is which stack do you use to unstack? This is important because you know we got two stacks, main stack and process stack. So when we unstack, we have to unstack correctly. If you stack with main stack, but you unstack with process stack, that's wrong already, right? So this tells the processor which stack to unstack correctly. Okay, so this is just the sequence. Right, now, one thing that you should always remember, this one a lot of people forget. And even now I tell you, right, you will definitely, some of you may miss this and you ask me again later when you get this problem. What's the problem? You forgot to clear the interrupt flag. You know, if you don't clear the interrupt flag, you will be stuck in the interrupt service routine. That means when you exit the interrupt service routine, immediately you will go back in again because the interrupt is still active. So the programmer needs to manually clear the interrupt flag. Pulse interrupt, no problem lah. It's the level triggered interrupt that is a problem because it's level. Level means like this. When the interrupt flag is set, it remains set. When the interrupt flag is set, it remains set until you clear it. So you have to manually clear it. Pulse, no problem. It's the level that's the problem. Okay, so you have to manually clear it before you leave the interrupt. So when you leave the interrupt, then you will do unstacking. This is the reverse of stacking. You do unstacking. So this one we look at the exception return. Just now, we look at the exception return bit too. You want to unstack with main stack or process stack. Okay, after decided already, then you start unstacking. So unstacking, you unstack um, uh, from top first. So you unstack from XPSR R0. No, you not from the top. This is a bit special. You unstack from XPSR first, then you go back down and unstack from R0, R1, R2, R3, R12, LRPC in this order. Why in this order? You have to ask the designer. That's how they create it. All right. So after the unstacking is done, right? Then you have to check XPSR bit 9. Remember just now, XPSR bit 9 indicates padding, right? Indicates padding. So the stack pointer needs to be adjusted. You remember here just now? You remember here? So after stacking, your stack pointer is SP minus 32, right? So after unstacking, your stack pointer needs to plus 32. You need to reset the stack pointer. You need to plus 32 when you unstack. If you got padding, then it's not 32. You have to plus 36. When you stack, your stack pointer become minus 36. When you unstack, you have to adjust it back. You have to plus 36. You've got padding. If no padding, plus 32. Okay, so that's why you see that's why the processor refer to this. Okay, then it will check the exception return bit 2 to see whether it should uh, set the stack pointer back to MSP or PSP. Okay, because just now just now here here you unstack with MSP or PSP, right? So after you unstack already, then you need to set the stack pointer back correctly to the original, the one that was used before the interrupt. Okay, so you have to set the stack pointer back correctly to the stack that was used before the interrupt happens. And then you fetch the return address, which is the unstacked program counter. Program counter is the next instruction to execute. Just now when the interrupt happened, you stack it already. So now you unstack it already. So the unstacked program counter will actually be allow you to resume your interrupted program. Okay, all right. Now we have a few mechanisms to speed up interrupt response. There are three mechanisms to speed up interrupt response. The first one is called late arrival. Let's say an interrupt happens, so the processor is doing the stacking. This will take some time because you have 8 registers, 4 bytes each. 8 times 4, 32 bytes. You got 32 bytes of memory access here. So it takes some time. So while this is happening, if another higher priority interrupt comes, then your processor will process the higher priority one first. Okay? If you do not have the late arrival mechanism, what happens? I give you an analogy. Let's say your mom tell you now, go to the supermarket, buy some vegetable. Okay? Go to the supermarket, buy some vegetable. Okay, so you go to the supermarket. When you reach the supermarket, you buy vegetable, right? Then your mom call you again. Buy meat also. So then what do? Without late arrival mechanism, you won't buy the meat. You just buy the vegetable. Then you go back home. You go back home, then you go to the supermarket again to buy the meat, right? This is this analogy. So here, without late arrival, it would be you do stacking. After you do stacking, right, for the low priority, then you do stacking again for the high priority. Okay? If you got no late arrival, you do stacking the first time, right? And then you stack again for the high priority. So it's like you go to the supermarket, uh, you buy the vegetable, then you didn't buy the meat, you go back home first, and then you go to the supermarket again to buy the meat. So it's waste of energy, right? So what happens is, if we process the high priority first, then you don't have to stack and unstack. You know, just now you just stack one time, right? After stacking one time, instead of running the low priority, you immediately run the high priority, right? What happens after you run the high priority? Then we call it tail chaining. Tail chaining is, right, after the processor finish running an exception handler, it will check are there any pending exceptions. If there is, the processor does not unstack. It will straight away fetch the vector for the pending interrupt and then tail chain. Proceed and run the next one without unstacking. Okay? So all these mechanism is actually, we just want to avoid stacking and unstacking unnecessarily. The third one is called pop preemption. Pop preemption. You see, while you are unstacking, if another interrupt comes, what happens? Do you wait until the unstacking finish? No. The processor will abandon the unstacking. It will stop the unstacking that is happening halfway and immediately go and respond to the new interrupt. Okay? Doesn't waste time unstacking here when another interrupt comes along anymore. So you got three mechanism. Late arrival, uh, tail chaining, and pop preemption. You got three mechanisms to reduce stacking and unstacking unnecessarily. Okay. All right. So now we understand the interrupt sequence already. Let's look at some examples. So here I have this is the very simple example first. This is a special timer inside your processor. We call it the sys-tick timer. So the sys-tick timer, you got 4 registers. You got the load register, which is now this is a 24-bit countdown timer. The normal timers, the PIC microcontroller, last time you learned the normal timers is a count up timer, right? Count up. When you count up and overflow, you generate interrupt. So this guy is different, right? This is a countdown. When you count down from 1 to 0, then you will generate an interrupt. Okay, so this is the reload value. So every time you count down to 0, when you underflow, 0 will underflow back to the reload value, right? Just like a PIC microcontroller, when you count up and you overflow, you will overflow back to the reload value, not overflow back to 0, like overflow to the reload value. So here, 24 bits, once you count from 1 down to 0, down to 0, you will generate an interrupt, right? And at the same time, you will reload. So this is the reload value. This is the current count value. Right? So how you access, this is the data structure. Sysdig arrow operator load is to get to change the reload value. Sysdig under arrow operator VAL is to get the current value. Okay. Now this is the control register. The control register bit 0 enables the counter, starts counting. Bit 1 is to enable the interrupt. Bit 2 is to select the clock source. So the clock source, there are two possible options. One is the internal CPU clock. If you put 0, then you're using the external clock that you feed in at a special microcontroller pin called STCLK pin. You only have this if the microcontroller support it. Some microcontroller does not support external clock for system timer, so you always have to use the internal clock. Okay, right. And this bit 16 is the interrupt flag. So if an interrupt happens, the interrupt flag is set. This is what we mean by level triggered. Level triggered. So this interrupt flag, once it becomes 1, it will remain 1 until you clear it. So how do you clear this one? By reading this register. Okay, cleared when read. So you can clear this interrupt flag by reading this register, or when you clear the this current value register, or when the current counter value is cleared. Okay, two ways to clear the flag. Right? Okay, this one not important on the calibration register. All right, so let's look at some code. Let's look at some interrupt coding. So I want to program for interrupt now. I want to write a program for interrupts. How do I do it? Now, let's say I want to generate an interrupt every 0.1 second. I want to generate an interrupt every 0.1 seconds. Okay, so my processor clock is 1 million. My processor clock is, 100 million. 100 million. The processor clock is 100 million pulses per second. 100 megahertz. 100 million pulses per second. That means you will have 100 million clock pulses every 1 second. Okay, 100 million clock pulses every 1 second. So 0.1 second means 10 million clock pulses, right? So the reload value, you see here, I need to program the Sysdig timer. First, the control register, I put 0 to disable the timer. Disable it first. You must stop the timer first. Then I put into the reload value, the correct reload value. What's the correct reload value? This is 100 million. System call clock. System call clock is a standard variable for your processor clock. Okay, so system call clock in this case would be 100 million. Of course, you can put 100 million here, but it's better to use system call clock. System call clock is the variable that represents your processor clock frequency. Okay, so 0.1 times 100 million is 10 million. No? You have to put 10 million into your load register, right? Because every 10 million clock pulses correspond to 0.1 second, right? 100 million clock pulses correspond to 1 second. So 10 million clock pulses is 0.1 second. So we have to put 10 million in the reload value. So after every 10 million clock pulses, 0.1 second has passed, right? Okay, so that's why the reload value is 10 million. Then we put a 0 to clear the current value, and then we start the Sysdig timer. Now, when you start the Sysdig timer, it will start from 0, right? And then it will underflow to your reload value. That's why we -1 here. Okay, you see your Sysdig timer start from 0, man. If you start from 0, then immediately on the next clock, you will reload. You will reload to 10 million -1. Why -1? Because we have to spend one extra cycle here starting from 0, right? So it will be 0, and so the first clock cycle it will be 0. Then the next clock cycle it will be 99 1,999,999 thing lah. Okay. So you put 7 here to enable the timer, interrupt, and use CPU clock. So it looks like a lot of work here. So I tell you a simpler way to do it. Instead of writing these 4 lines of code, you can just use the sysdig function. This is a CMSIS core function provided by the CMSIS library. It's already inside your project one, automatically added one. You just type sysdig 0.1 multiply with system call clock. It will automatically minus 1 inside already, so you don't have to do anything extra. So now let's say your assignment you want 2-second delay, right? You want to change the light, the color every 2 seconds, right? So why don't you program the sysdig timer to generate an interrupt every 2 seconds? How we do that? Sysdig 2 multiply with system call clock. Right? Sysdig 2 multiply with system call clock, and immediately uh, the system timer will generate an interrupt every 2 seconds. So what happens when the system timer generates an interrupt? Processor will stop whatever it's doing and run the sysdig handler code. So then you put here the IRQ processing here, you put your code to change the RGB color, and always remember before you exit the sysdig handler, the interrupt handler, always remember to clear the interrupt flag. Why we do this? We call this a dummy read. A dummy read. I read from the same register back into itself. It's a dummy read, which means I didn't do anything. But why I need to read this? It's because I need to clear the interrupt flag. Remember, you you clear this flag by reading this register. You cannot write a 0 here. You need to read this register to clear this flag, to clear the interrupt flag. So this is just a dummy read to clear the interrupt flag. Okay. Otherwise, you'll be stuck in the interrupt service routine. Okay, so this is one example. Now I have another example here. I leave you to read this. Here, there is another example here. Okay. So I have 2 example interrupt programs here. Just give me a minute. Just give me a minute. So I have 2 example interrupt programs here. Okay. Um, what happens is I have a button and an LED. When you press the button, you will toggle the LED. Toggle means you press the button, the LED turn on, press it again, the LED turn off, press it again, the LED turn on, press it again, the LED turn off, and so on. Okay. And I don't want to write a program where I keep checking this button. I don't want to. I want to use interrupt. So when you press the button, an interrupt is generated. How do we do this? All I/O ports come with interrupt function one. All I/O ports come with interrupt function. Okay, so for the LPC1768 is a bit limited. For LPC1768 is a bit limited. Why? Because interrupts, GPIO interrupt at IO pin is only at these 4 pins. Port 2 bit 10, port 2 bit 11, port 2 bit 12, and port 2 bit 13, which corresponds to external interrupt 0, 1, 2, and 3. Only got 4 external interrupts. So if you want external interrupt, right, you must connect to these 4 pins. But STM32 is much more flexible. STM32, you can connect an interrupt to any GPIO pin. All GPIO pins, are interrupt capable. But then the price to pay is a bit more complex programming. Right? See here, you start programming for LPC1768 already. For this guy, you need 6 steps. 1, 2, 3, 4, 5, 6. This guy only 1, 2, 3, 4 steps. So the SM32 got a lot more programming steps because you have lots more flexibility. Okay, right. So this would be your assignment. I have the code here. You see the nice. So if you understand this and the code, you can use this for your assignment, right? You can use this for your assignment. Okay, I'm out of time to discuss the quiz. So let me just check with you guys. Do you have a class at 3 o'clock? Class, do you have another class at 3 o'clock? No, no, okay. Just give me 5 minutes, just give me 5 minutes, and I go through the quiz answer with you. Just give me 5 minutes. Okay, let's look at the quiz now. Who hasn't submitted? Two more hasn't submitted. Okay. Uh, Boon Kyung, are you here? Ku Boon Kyung, are you here? Okay, great. Full attendance. Thanks. Right. Now, if I haven't called your name yet, or you must remind me. If you come maybe 5-10 minutes after the class started, then at the end of the class, please remind me to take your attendance. Right. I might forget sometimes. So who haven't submitted yet, please submit. Because I need I use this to take your attendance for your lecture. Okay. So I will take your attendance if you have submitted the quiz for the lecture on Tuesday. Right. Okay, let's look at the quiz now. Let's look at the quiz. Okay, now, first one. Why is interrupt masking only removed after the interrupt configuration? This is very logical because when you are configuring the interrupt, you will disable the interrupt, right? Interrupt masking means you are blocking this, you are disabling the interrupt. So obviously, when we are, when you fix the electrical product, obviously you turn off the power first, right? You turn off the power, you fix the electrical circuit, fix already, close back everything, only you turn back on the power, right? Otherwise, something bad might happen. Same here. If you are programming the interrupt, obviously you disable it first. After you finish programming only, you enable it back. So you prevent incorrectly triggered interrupts, right? If you didn't disable the interrupt, then the interrupt may be triggered while you are configuring, and that would be incorrectly triggered, right? So you don't want to service incorrectly triggered interrupts. Okay, next one. Which of the following does not contribute to prevention of race condition? Okay, so I tell the story of race condition. Race condition race condition is you're fighting with your little brother or little sister. Let's say you have one, you're fighting with them. So your little brother or little sister says, "No, the ball should be on the table." So he put the ball on the table. Then you said, "No, the ball should be on the floor. We don't put the ball on the table. We kick it on the floor." So you put the ball on the floor. Then he said, "No, ball should be on the table." You put it back on the table. So I ask you, in the end, is the ball on the floor or on the table? In the end, the ball, is it on the floor or is it on the table? So this is a race condition, right? It's a race condition because the ball will be either on the floor, on the table, or depending on the last person who touched the ball. If you were the last person who touched the ball, then the ball will be on the floor. If your little brother or sister is the last person to touch the ball, then the ball will be on the table. So it's a race, right? You see who is the last person who can get the ball. So it's the same here. Now, a race condition is where you have a variable, right? And you are modifying the contents of this variable. What happens is, in the middle of modifying the contents, an interrupt happens. The interrupt also modify the variable that you are modifying. Problem, right? You see, you are modifying a variable. It's like you are moving the ball. Okay? But while you are moving a ball, somebody else can move your ball. So what happens? What happens? What is the value? What happened to the ball? Right? The ball can end up half on the table and half on the floor. Anybody laughing? You catch the joke, right? Because you see, a variable is not 1 byte. In a 32-bit machine, a variable is 4 bytes. So 4 bytes means you can actually change in each individual byte. Or I give you a better example, an array. Let's say I got an array of four integers. While I'm changing the value of these 4 integers, an interrupt happens, and then the interrupt go and change the value of one of the variables. So then after that, the interrupt is done, return back to me. I didn't know that the interrupt did something. I didn't know, so I continue. So what happened now is the value that I'm modifying has been corrupted, right, by the interrupt service routine. I don't know, because I didn't know the interrupt has happened. Okay, it's just like a ghost. Go and move the ball. You don't know one. Okay, so how do we prevent this from happening? How do we prevent data corruption by interrupts? We just disable the interrupt. So if you're doing something important and you don't want to this modification to be corrupted by the interrupt service routine, you just disable interrupts. All right. So preventing race condition means one of the simplest method is just disable interrupts. Right? Interrupts are the things is the thing that cause race condition. So how do we disable interrupt? We can use the priority masking register to disable interrupts. We can use CPS IE, CPS ID instruction to disable interrupts. We can use ISER, ICER to disable interrupt. Control register cannot disable interrupt lah. Right? So which of the following does not contribute to prevention of race condition? Control register. Okay. Right. When a global variable may be modified by an exception handler, it should be declared as volatile. Right? Volatile is when you have variables that can be modified outside of processor control. Okay? So you have some variables that although the processor never changed the value of this variable, right? The value may change one. Why? Because it can be modified by interrupt service routine, or it can be modified. For example, it's your GPIO. Let's say your GPIO is connected to push button. So when you press the push button or you release the push button, you will change the value inside the GPIO register, right? And processor never do anything. So such variables whose values can be modified outside processor control, you must put a volatile to prevent the compiler from optimizing the code, to prevent the compiler from changing the code uh, from what you intended it to be. So you have to put volatile here. Okay. All right, next one. This is the sequence. What is the sequence of uh, things that you push into the stack when an interrupt happens? So it's this sequence actually. This is the sequence. This is the sequence. When you push things into the stack, right? You will go R0, R1, R2, R3, R12, LR, PC, XPS. This sequence. Starting from R0 until XPSR. So this is the sequence. R0, R1, R2, R3, R12, LR, PC, XPSR. Okay. Right. That's pretty straightforward. Okay, next one. Which of the following statements about preemption is correct? Preemption. Preemption. Configurable priority has precedence over negative. Wrong, right? Configurable priority is 0 to 255. Negative priority is higher than 0. So configurable priority cannot have precedence over negative priority one. This is wrong. Okay, next one. Higher IRQ number has precedence over lower IRQ number. This is also wrong, right? Lower IRQ number is higher priority than higher IRQ number. The next one. Higher group priority has precedence over lower group priority. This is correct. Okay. Higher group priority. Now, I didn't mention number here. Higher group priority means the group priority number is smaller. Higher group priority means that the group priority number is smaller. Okay. Smaller group priority number means higher group priority, which of course can preempt lower group priority, right? Higher sub priority has precedence also. No. When you have preemption, sub priority doesn't matter one. Right? Sub priority is not important. When you talk about preemption, you have to look at the group priority, not the sub priority. Right? Okay. Uh, which of the following does not contribute to interrupt latency reduction? Interrupt latency means the delay of the processor responding to interrupts. Interrupt latency is the delay of the processor responding to interrupts. So which one contribute to reduction? Now, vector fetch is, because vector fetch is hardware. Hardware means is done automatically by the circuit. The circuit there is some special circuit that will do it automatically for you. This is what we call hardware. Okay, software means you have to write code to do it manually. When things are done in hardware, automatically, this means it's faster. Right? When you do things in software, it's very slow because you are subject to the processor clock. Slower processor clock means slower. Faster processor clock means faster. But when you do things in hardware, you are not subject to the processor clock. You are just subject to the electron speed moving through the circuit. Right? When you do things in hardware, you are just subject to the speed of the electron moving through your circuit. Okay, so vector fetcher speeds up. This is done in hardware, so you speed up fetching of interrupt series, the interrupt address. Pop preemption speed ups the interrupt response because if the interrupt comes when you are unstacking, you can just abandon the unstacking. Okay? Hardware stacking also speed up your interrupt response because this is done in hardware. You don't have to do stacking manually in software. Okay. Now, what does not contribute to interrupt latency reduction is stack auto alignment. Right? Stack auto alignment, if you need to insert padding, it actually takes up more time to insert the padding. Okay, so it doesn't help with interrupt latency reduction. Okay. All right, next one. Which of the following statements regarding supervisor call is not correct? Now, supervisor call must execute immediately. If you execute the SVC instruction, the supervisor call handler must run immediately. Okay, if you execute the SVC instruction, the supervisor call handler must run immediately. What happens if you go and execute SVC inside the SVC handler? What happens if you execute SVC inside the SVC handler? If you execute SVC, you must immediately run the SVC handler, right? But if you're already inside the SVC handler and you try to execute SVC, that means you cannot run SVC handler immediately. You have to wait until you exit this SVC handler, then only you can go back in again. So you cannot execute SVC immediately from the SVC handler, right? So this is not correct. If you execute SVC instruction, you cannot execute immediately from SVC handler. Right? You have to wait until you exit the SVC handler before you can go back in and execute again. Okay, so this is not correct. Right? Okay, next one. This is the last one. So I have 3 interrupts. Interrupt 0, interrupt 1, and interrupt 2. So 0 has highest priority, 1 medium priority, 2 is the lowest priority. Then I got thread code running. Okay, so interrupt happen as follows. Interrupt 2 comes along, so the processor respond to interrupt 2. While the processor is responding to interrupt 2, or interrupt 1 and 0 comes along. So what is the following sequence? Okay, first of all, thread is preempted by 2, right? Because first of all, you're running thread, and then 2 happens. So thread is preempted by 2. Then, while you're responding to 2, 1 and 0 comes. Who is higher priority? 0 is higher. So 2 will be preempted by 0. Okay, 1 is pending. Then when 0 finishes, 0 will tail chain to 1. Right? And then when 1 finishes, 1 will return to 2. And then when 2 finishes, 2 will return back to thread. Okay. All right. So good job, everyone. That's a lot of information to digest. So don't worry, take your time to digest it. All right. Read the lecture videos again. Read the lecture discussion notes again. Watch the lecture videos again. Okay? Take some time to digest it. Don't worry if you don't understand the first time. You need some time to digest one. In fact, it's normal that you read the first time, you only understand 25%. Then you read the second time, you understand 50%. You read the third time, you understand 75%. You read the fourth or fifth time, only you fully understand. Okay, or maybe 95%, not still not fully understand it. But you need to read. Okay. Maybe you read this week, you don't understand. You keep reading every day, bit by bit, you start to understand. By next week, you understand already. So the important thing is you must read. Okay, you must read, and then don't worry if you cannot fully understand. Just read and make sure every time you read, you understand a bit more. Okay, and those things that you are really stuck at, you just cannot figure it out. Just email or WhatsApp me. Okay. All right. So good job, everyone. Thanks for coming today, and I'll see you in the next class. Okay. Tiong Lia's question, no? Group priority lah. Level 5 has higher priority than level 1. Smaller number is higher priority. Okay, smaller number is higher priority. So 1 is higher priority than 5. Okay, group priority of 1 is higher priority than group priority number of 5, the value lah. Okay, all right. Yes, smaller value has higher priority. Smaller value has higher priority. Okay, yes.